Hi everyone, we are from Group K. We will present about our project, Basic Passive Low Pass Filter. This is our group member, Muhammad Nur Faiq bin Noor AZIAN, Muhammad Danial bin Ahmad NORDDIN, and I am Zulhanif bin ROZALI. And our lecturer for Advanced Electrical Circuit is Dr. Muhammad Shahril bin Yahya. Okay, this is group member role for Group K. Muhammad Nur Faiq bin Noor AZIAN as a group leader, Muhammad Danial bin Ahmad NORDDIN as a circuit drawing engineer, and Zulhanif bin ROZALI as a test engineer. For abstract of our project, low pass filter. A low pass filter is a circuit that can be used to modify, restructure, or reject any undesirable high frequencies in an electrical signal while accepting or passing just the signals that the circuit designer wants. In other words, filter out undesired signals, with an ideal filter separating and passing sinusoidal input signals based on frequency. Passive filters are often built with simple RC network in low frequency applications up to 100 kHz and RLC, resistor inductor capacitor, components in higher frequency applications above 100 kHz.
Hello, Assalamualaikum to everyone, especially to Dr. Muhammad Shahril. My name is Muhammad Danial. Me and my friend are going to present to you about the basic passive low pass filter. My friend name are Muhammad Nufai and Zulhanif. I'm going to present to you about the introduction. A low pass filter allows signal and with frequencies lower than a preset cut-off frequency to pass while attenuating signals with frequencies higher than the cut-off frequency. The frequency response of the filter is determined by its design. In audio application, the filter is known as a high cut filter or treble cut filter. The complement of a high pass filter is a low pass filter. The low pass version is frequently used as a prototype filter by filter designers. That is a filter having the same bandwidth and impedance as the input signal. By scaling for the desired bandwidth and impedance and translating into the desired bandform. The desired filter can be obtained from the prototype that is low pass, high pass, band pass, or band stop. The cut-off frequency or break frequency FC is the frequency at which a low pass filter begins to attenuate, lower the amplitude of a signal. The cut-off frequency is defined as the frequency at which the output voltage amplitude is 0.707 of the amplitude of low frequency signal. The cut-off frequency is also known as the half power or 3 dB down frequency since it corresponds to half power. Because the algebra is rather simple, cut-off frequency are usually calculated as C in radians per second when working with measurement. However, it is preferable to utilize frequencies represented in Hertz as FC. The cut-off frequencies for an RC low-pass filter are given as follows. This is the formula that has been given for the RC low-pass filter. For an RL low-pass filter, the cut-off frequencies are FC equal to WC omega C divided by 2 pi, or it can be proven by resistor divided by 2 pi L. The frequency response of a filter circuit is typically represented by 2 semi times 0002 logarithmic graph, each with a different axis horizontal axis that represent the frequency on a logarithmic scale. The voltage gain in decibels is shown on one graph, while the phase shift of the output voltage with respect to the applied input voltage is shown on the other graph ordinate vertical axis. Finding the transfer function TF of a particular filter yields the voltage gain and phase shift for every frequency. The ratio of the output voltage phasor to the input voltage phasor is the transfer function. H, that is omega, equal to V out divided by V in. Now I'm going to tell you about the procedure of low pass RC filter circuit. We need to combine a resistive and a reactive element to make a passive low pass filter. To put it another way, we will need a circuit with a resistor and either a capacitor or an inductor. In theory, the resistor inductor RL low pass topology is equal to the resistor capacitor RC low pass topology in terms of filtering ability. However, because the resistor capacitor variant is far more prevalent in practice, the remainder of this essay will concentrate on the RC low pass filter. Okay, for the procedures, firstly, assign the value for the passive component which resistor 1 equal to 330 ohm and capacitor 1 equal to 0.47 microfarad. Secondly, derive the transfer function H equal to V out over V in and explain the type of transfer function: voltage gain, current gain, transfer impedance, or transfer admittance. Next, provide the zero end pole that is available for the circuit. The fourth is calculate the frequency FO. And the fifth, figure 1 show how to put together a circuit, connect the oscilloscope channel 1 to the input voltage V in and adjust V in to a frequency of 100 Hz with an amplitude of 2 Vp equal to 4 Vp 2 peak on the oscilloscope display. After that, connect the generator of the oscilloscope to the capacitor C. For the output voltage V out, measure the amplitude Vp. Table 1 should provide the result. The next one is increase the function generators frequency to the frequencies listed in the table 1. Adjust the amplitude of the function generator if necessary to keep V in at 2 V peak equal to 4 V peak to peak on the oscilloscope display. For each frequency, calculate the amplitude V peak. And lastly, adjust the frequency of the function generator until V out 0.707 times with V out max to get the cutoff frequency FC. Make a note of the measured cutoff frequency in table 2 below. Okay, that's all for me. I will pass the next one to my friend.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Nur Faiq bin Noor AZIAN and I am the leader of Group K. I will further our presentation with our result. Firstly, we assign the value of resistor 1 equal to 330 ohm and capacitor 1 equal to 0.47 microfarad. Secondly, we determine the transfer function TF for RC low pass filter circuit of figure 1 in the previous slide, where we got the value of TF equal to 1 over 1 plus j omega over 6.45k, where the value of 6.45k is from the 1 divided by RC, as from figure 3 above. A low-pass filter is an electronic device that permits low-frequency AC signals to flow current to the filter circuit, as the name implies. Depending on the frequency of the input signal, the filter circuit's output will be attenuated. Filter circuits with diverse properties can be built using a variety of active and passive components. Defining a transfer function is the simplest approach to summarize the behavior of a filter. At various frequencies, the transfer function shows how the output signal is connected to the input signal.
A graph of the output signal at various frequencies can readily be used to estimate the transfer function when designing a filter circuit. We may also use Kirchhoff's rule to obtain the differential equation that regulates the circuit by calculating the transfer function. The figure below are the derivation to find the transfer function. When a signal goes through a filter, the output signal will be phase shift in relation to the input signal. This means that the filter's transfer function is a complicated function of frequency, and the transfer function contains all of the information needed to calculate the output signal's magnitude and phase. The graphic in the previous slide depicts the broad definition of a transfer function, as well as its magnitude and phase. Once you know a filter's transfer function, you can convert it to a dot plot to see the transfer function in decibels. After that, we determine the theoretical cutoff frequency for the figure 1 to record the values in the figure 4 below. This step is very important for us because we need to know the value of cutoff frequency, as we need to measure it later, and the value of it must not be different with theoretical one, as from the figure 4 in this slide. Then, in step 4, we sketch the straight line approximations of the frequency responses by using the value from the steps 3. From the figure 4 above. Figure of the graph below is an example for our sketches in the next slide. So, the figure 5 and figure 6 above are the sketches of the straight line approximations of the frequency responses. Furthermore, in step 5, we insert the V out by using the simulation from the multisim to calculate the voltage gain, as AV equal to V out over V in, and AV in decibel equal to 20 log V out over V in. To find V out, we simply just adjusting the value of frequency and amplitude in the function generator and make sure the channel 1 V in stays at 4 volt peak to peak. As you can see, every frequency has different output of V out. So this step is done to complete the dot plot. Figure 7 until figure 12 below is the proof that we use simulation to find V out. As you can see, we adjusting the frequency and amplitude to find the V out from the channel 2. The channel 1 V in, which is volt peak to peak, must stay at 4 volt. Moreover, in the step 6, we find out the cutoff frequency, which is FC, from the equation of V out equal to Vmax times 0.707 volt. The Vmax 2.01 volt is from the table 1 in the previous slide. So from the figure 13 below, we simply just adjusting the value of frequency until the V out of the channel 2 is equal to 1.42 volt, as from the equation Vmax times 0.707 volt. We got 1.42 volt, and we need to adjusting the frequency until the V out of channel 2 is 1.42 volt that we got earlier. For that, our measured cutoff frequency is 1 kHz. However, the channel 1 V in must stay at 4 volt peak to peak. Lastly, we plot the data AV in decibel versus frequency of table 1 on graph 1. We simply connected the points with the best most continuous curve. So the graph 1 below shows our dot plot of voltage gain response. As you can see, the cutoff frequency is at 1 kilohertz. I will further our presentation with simple simulation videos. So as you can see here, this is our low pass filter circuit. This is the function gen and this is the tectonic oscilloscope that we already connected to the circuit. So what we need to do here is just simply click on the run simulation button here. So as you can see, the tectonic oscilloscope already shows a waveform. I already clicked on the auto set and the measure button, and I already set the value here to find the out. Alright, so let's say if I want to change the frequency to 1 kilohertz, right? So as you can see here, the channel 1, which is V in, is 3.96 volt peak to peak. This is not the value that we want. We want to adjust it until it stays at 4 volt peak to peak. So what we need to do is just simply click at the amplitude and then simply adjusting the value of the amplitude in the function gen above until we get the channel 1 to 4 volt peak to peak. Alright, so after we got the 4 volt peak to peak value in channel 1, this value on the channel 2 here, which is V out, this value is the one that we need to insert in the table 1 previous. So that's all.
For the discussion, the RC low-pass filters are the most important things we learn in this assignment. A low-pass RC filter is a filter made up of a resistor and capacitor that allows low-frequency signals to flow through while blocking high frequency. To make a low-pass RC filter, connect the resistor in series with the input signal and connect the capacitor in parallel with the input signal. To construct a passive low-pass filter, we will need to combine a resistive and a reactive element. We will need a circuit with a resistor and either a capacitor or an inductor. To put it another way, in terms of filtering ability, the resistor inductor RL low-pass architecture is theoretically equivalent to the resistor capacitor RC low-pass topology. The remainder of this essay will focus on the RC low-pass filter because the resistor capacitor type is significantly more common in practice. As for the results that we obtain from the simulation by using the multisim, the things that happen when frequency is increased, the output voltage V out and phase angle will decrease according to the RC low-pass filter measurement. We obtain the results by adjusting the function generator and observe the value in the tectonic oscilloscope. Lastly, our circuit is designed to be used to modify, restructure or reject any undesirable high frequencies in an electrical signal, while accepting or passing just the signals that the circuit designer wants. Lastly, for the conclusion, we were able to determine the transfer function and cutoff frequency for a low-pass filter by the end of this assignment. The cutoff frequency is defined as the frequency at which the output voltage amplitude is 0.707 of the amplitude of low frequency signals. The cutoff frequency is also known as the half power or 3 dB down frequency, since it corresponds to half power. The frequency response for a low-pass filter circuit was also computed by us using straight-line approximations of the both plot. Finally, we were able to compare the real frequency response with approximation of frequency response. That's all from our group. Thank you.